with that, let us start the seminar, and let me introduce our speaker, Professor Dr. Theodor Haensch, truly a living legend in the field of precision measurements and fundamental physics, who received the 2005 Nobel Prize in Physics. So Professor Haensch graduated at the University of Heidelberg in the 1960s. Subsequently, he moved to Stanford, where he was working as a professor from 1975 to 1986. And in 1986, he returned to Germany to head the Max Planck Institute for Quantum Optics in Garching. Professor Haensch has dedicated his scientific life, passion, and creativity to the development of ultra-precise laser spectroscopy techniques. This involved the invention of really numerous groundbreaking spectroscopy methods, among those the invention of the frequency comp technique, which culminated, for example, in precision spectroscopy of the hydrogen 1s2s transition at the 10 to the minus 15 level. So Professor Haensch has influenced an entire generation of precision physicists, which triggered many additional groundbreaking inventions. And it's needless to say that for his work, he received numerous additional research prizes. It's our honor, Professor Haensch, that you have decided to give a talk in the seminar today. Professor Haensch will be talking about work towards a solution of the proton radius puzzle. We are very much looking forward to your talk, and with this, I leave the floor to you. Thanks very much.
Thank you very much for this kind introduction. I'm impressed by how many people are watching, and I hope you all succeeded to survive the pandemic without harm. I got my second vaccination shot the day before yesterday, and so I hope it will help that we all can go back to a more normal life and can meet in person again without masks. But so let me try to share the screen. So I had promised to talk about where we stand on our way to solving the proton radius puzzle. And I will not just talk about that, but remind you of the important role of precision spectroscopy of hydrogen in the history of physics and quantum mechanics. As scientists, of course, we like to discover something new. Students asked for a recipe. How do you do that? And one advice, which of course doesn't work always, but which enhances the chances, is to look where no one has looked before. And in particle physics, that means looking at higher and higher energies to maybe discover some limits to the standard model. But another approach that is closer to my way of working is to make measurements with higher and higher precision, in the hope that we can also find some limits to our understanding of the fundamental laws of quantum physics. And if we look back, precision spectroscopy in the past has really been a key to deciphering the riddles of atoms and quantum physics. It started maybe back in the 19th century when Kirchhoff and Bunsen, two chemists, showed that if you look at the light emitted by some chemicals in the flame, that you can see sharp lines that seem to be characteristic for different elements. And so, like fingerprints, it's a way to identify different elements. Of course, at that time, people had no idea how these spectral lines come about. The simplest spectrum that you can study is that of the lightest of the atoms, the hydrogen atom. And so it's an impressively regular spectrum. And Balmer discovered that you can describe the wavelengths in the spectrum by a simple formula, which was later generalized by Rydberg. And in this context, he introduced the Rydberg constant, one of the fundamental constants. But at this point, still, people had no idea what is going on. That had to await the discovery of the atomic nucleus by Rutherford. And once the construction of an atom was understood, Niels Bohr came up with his planetary atom model, where you assume that you have stationary orbits of the electron, that radiation is emitted or absorbed in quantum jumps. And it was clear that this model had many shortcomings, but amazingly, it was able to express the Rydberg constant in terms of other known fundamental constants. So something was right. Louis de Broglie speculated that these stationary orbits might be those where an integer number of matter waves, of the Bohr waves, fit into the orbit. And then Schrödinger came up with a wave equation for these matter waves that could be solved in closed form for the hydrogen atoms, and that really not only allowed one to calculate the wavelengths and energy levels, but also the transition probabilities and polarization and things like that. So that was a tremendous breakthrough, and it was really the Balmer spectrum of hydrogen that was the Rosetta Stone for deciphering the non-intuitive rules of quantum mechanics. Sommerfeld knew that the Schrödinger theory cannot be totally right, or the Bohr theory, because if one looks closely at the, for instance, Rydberg Balmer-alpha line of hydrogen, it's not a single line, but it shows some fine structure, some suspected 3 components, which Sommerfeld tried to interpret in terms of Bohr orbits, but now also elliptical orbits. And so in this context, they introduced the famous fine structure constant alpha. And then Dirac succeeded in writing down a relativistic generalization of the Schrödinger equation, the famous Dirac equation, that not only predicted the fine structure of hydrogen lines, it even could describe anti-electrons, positrons, and it seemed so beautiful that this was considered the ultimate formula for explaining the quantum world. In the 30s, people had some nagging doubts whether the Dirac theory really described the line profile of the Hydrogen Balmer-alpha line. But this question was not settled in the end by optical spectroscopy, but by microwave spectroscopy of a metastable hydrogen beam, where Willis lamp discovered what's now known as the lamp shift, the fact that 2 energy levels that should be precisely the same according to Dirac, the 2s state and the 2p state, are in fact split. They're not the same. And Hans Bethe was the first to give an intuitive explanation for this lamp shift. He said it's a manifestation of the interaction of the atom with the vacuum that is neglected in the Dirac theory. In the vacuum, even at absolute zero, we have vacuum fluctuations that wiggle around the electron. So from the point of view of the electron, the nucleus appears smeared out, and therefore the S state, where it comes close to the nucleus, is less tightly bound than the P state. Another effect of the opposite sign, but smaller, the effect of vacuum polarization. That vacuum can behave like a dielectric because you can create virtual electron-positron pairs. So that was okay. That was the beginning of quantum electrodynamics and the prototype of modern quantum field theories. So that's the old history of hydrogen spectroscopy. And then a new chapter was opened by the advent of the laser. In 1958, Art Schorlow, my mentor at Stanford, and Charles Towns published a seminal paper where they proposed a way to make optical masers, masers that operate at wavelengths of visible or infrared light. And this triggered a race to realize the first laser. And this race was won in 1960 by Ted Mayman with his famous pulsed ruby laser. But of course, now there are many, many lasers, and lasers have really revolutionized not only spectroscopy, but different fields of science. And as of now, I think we can count 32 Nobel Prizes with lasers or around the laser. So as I mentioned, Art Schorlow was my mentor at Stanford. I joined him as a postdoc in 1970, more than 50 years ago. And if you met him, he was a humorous person, very playful. He has a real little ruby laser with which he can pop a blue balloon inside and clear outer balloon that stays unharmed. If you would meet him in the hallway, often he asks you, "What have you discovered?" And for the student, that was an important message, that they're not really here to learn something old, but to discover something new. Well, most of the time one had to admit just now, yeah, I probably haven't discovered anything. But one day I could actually report that I had discovered something. And that is, I had played with a widely tunable dye laser. These were devices that had just come on the scene, pioneered by Fritz Schäfer in Göttingen and Peter Sorokin at IBM, where the active medium is a liquid solution of some organic dyes. And you can pump it, for instance, with ultraviolet flashes from a pulsed nitrogen laser, and you get enormous gains. So you don't have to be very careful with the cavity. Partly transparent mirror and the diffraction grating are enough to make a laser. And if you tilt the grating, you could, for this laser, change the color from yellow to green, or from red to yellow to green. So it was fairly spectacular. And the only disappointment was that the spectrum didn't look good. It was not laser-like, nice and monochromatic. And so playing with this, I wondered, yeah, this doesn't look like you're supposed to design a spectrograph. If you have a grating spectrograph, you have to make sure you illuminate the entire grating. So what about a telescope that expands the beam? And I had a little pocket telescope in my trouser pockets. So I mounted it, and immediately we had a laser that was remarkably monochromatic, not only widely tunable, but highly monochromatic. And with a little more engineering, it was a fabulous tool that opened up many new possibilities. In 1973, I was named, together with Art Schorlow, California Scientist of the Year for this invention. There were also California Industrialists of the Year. William Hewlett is shown here. His partner, David Packard, was in Washington at the time of the ceremony. But so his little trick not only opened a new field of laser science, it led to my tenure as a professor at Stanford University. And one of the first things to do with this new laser was to revisit the Rydberg Balmer-alpha line of hydrogen, but now by Doppler-free saturation spectroscopy. It's a technique that had been pioneered with gas lasers, where you have two counterpropagating beams going through an absorbing medium. One bleaches, the other one senses this bleaching, but only if the two interact with the same atoms that are either standing still or at most going sideways. So now here we had a saturation spectrum of the Rydberg Balmer-alpha line, And we could, for the first time, see resolved fine structure components. The classical spectroscopists others had to cope with a blend of unresolved lines because of the very large Doppler broadening for these light atoms. And so in particular, we could see the lamp shift directly resolved in the optical spectrum. And this really was the starting point for a long venture towards ever higher resolution and higher precision in spectroscopy of hydrogen. And here it stops at 2015, but I think the quest continues even as I speak. Laboratory experiments at Garching are continuing. And so in the early days, people could measure wavelengths to 7 digits, which was quite good for physics. But then with lasers and by eliminating Doppler broadening, we could push wavelength measurement to something like 10 digits. And then wavelength interferometry runs out of steam. So to make progress beyond that, we had to learn how to measure not the wavelength, but the frequency of laser light. And this is what has propelled us to something like 15 digits, where we are almost limited by how well we know our unit of time, the second. And the motivation for this ambitious adventure was that, of course, precision spectroscopy provides a way of testing bound state QED. And if there should be anything wrong with this theory, this might be a way to discover it. If quantum electrodynamics is right, it's a way to determine fundamental constants, in particular the Rydberg constant, one of the cornerstones in the system of fundamental constants, but also the proton charge radius. One can ask questions: are constants constant, or are they slowly changing with time? And then, of course, with hydrogen, we also have antihydrogen. So the question is, if you compare hydrogen and antihydrogen, are they precisely the same, or are there possibly differences? The slightest difference would violate the standard model, and it would definitely signal new physics. And the question is, yeah, how precisely do you have to measure to arrive here at any difference? Well, we don't know. Maybe there is no difference, but clearly the farther we can push the precision of these kinds of measurements, the more likely we are to discover any flaw in our fundamental assumptions. The narrowest line in hydrogen is that of a 2-photon transition from the ground state to the metastable 2s state, which you can excite with ultraviolet laser light at 243 nanometers. And if you use counterpropagating beams, you cancel first-order Doppler broadening. The natural line width limited by the 2-photon decay lifetime of the 2s state should be 1.3 Hertz. About 30 years ago, we started to observe this line in a cold hydrogen atomic beam in a vacuum chamber. We still don't have good ways of laser cooling hydrogen atoms, even though it has been done, and even done for antihydrogen. But it's difficult. So our way out has been to take atoms from a microwave discharge dissociates water molecules and cool them by collisions with a copper nozzle mounted to a cryostat. And these atoms then travel collinearly in a standing wave field maintained between 2 mirrors. And after 10 centimeters or so of path, they reach a quenching region where an electric field can force them to emit Lyman alpha photons that one can detect. And well, 6 Kelvin sounds cold, but it's nothing by cold atom standards. The hydrogen atoms still move with something like 300 or 400 meters per second. And so to single out slower atoms, we have a chopper that periodically disrupts the laser beam, and we look at time-delayed photons. So those that can only come from cold atoms that are still around after some waiting time. And so with this, and a lot of very hard work advancing the art of measuring optical frequencies, in the late 90s, we could announce, after maybe 10 years of hard work, that we had measured the frequency of this 1s 2s transition to within 840 hertz. And at that time, it was the most accurate measurement of an ultraviolet or visible optical frequency. We could give a value for the Rydberg constant, which we could claim as the most accurate fundamental constant. We could, by comparing two different transitions, determine the lamp shift of the ground state of hydrogen, and at the time that was the most accurate test of quantum electrodynamics for an atom. And by comparing two different transitions, if you believe QED is right, we can also determine the charge radius of the proton, and by in similar experiments with deuterium, the charge radius of the deuteron, and all these radii were the most accurate values to date. So that was more than 20 years ago, and it's a result of a lot of hard work, and most of the work went into techniques to measure the frequency of light. Nowadays, measuring the frequency of light has become extremely easy, and thanks to the invention of the frequency comb that was announced by different journals at the turn of the millennium, this is a very nice tool that makes it possible to measure any optical frequency in the range hundreds to thousands of terahertz very precisely. It provides a phase coherent link between the optical and radio frequency region, and it provides a clockwork mechanism for optical atomic clocks where the pendulum is not made up of cesium atoms oscillating in the microwave range, but of atoms or ions oscillating in the optical region, 100,000 times faster, so we can slice time into much finer slices. A frequency comb, let me remind you, is basically some mode-locked laser where you have a cavity with a pulse of light bouncing back and forth, and during each round trip, a pulse is coupled out to produce a train of light pulses. If I take a single such pulse and send it into a highly resolving spectrometer, let me take a sip of water so that my throat doesn't dry out so much. Yeah, so if you send a single pulse into the spectrometer, you see a broad spectrum. The shorter the pulse, the broader the spectrum. But if you have two pulses, then you get interference fringes in the spectrum. So in some ways you could argue it's an analogy to the Young's double slit experiment, where you have two slits and on a screen you get interference fringes in space. Here you have two pulses separated in time and you get interference fringes on the spectrum. And the spacing between adjacent fringe maxima is just precisely the inverse of the time interval between the two pulses. So in a way, it's already a frequency comb, just two pulses. As you increase the spacing between the pulses, the teeth move closer and closer together. And the only problem is it's not very sharp. But now if I have a whole train of pulses from our mode-locked laser, and if I wait, then after a while, the spectrometer will show very sharp lines that can be as sharp as those of any CW laser, and still spaced very precisely by the repetition frequency of the laser. And so it's a simple idea, easy to explain. But what has surprised most experts is how far these principles could be pushed, that you could take a mode-locked titanium sapphire laser, for instance, broaden its spectrum in a microstructured silica fiber, where by self-phase modulation and soliton formation and other nonlinear processes, you produce white light that you can disperse with a grating into a rainbow spectrum, but not ordinary white light, but light that consists of 100,000 or of millions of sharp, precisely equally spaced spectral lines. And as I said, the spacing between two of these lines is just given by the repetition frequency of the laser. The overall comb is offset by some frequency that depends on the slippage of the phase from pulse to pulse. But if you have an octave spanning comb, it's possible to measure this slippage, and you can use servo controls to even make it go away. So then you have a frequency comb where each line is a precise integer harmonic of the repetition frequency, which you can measure with a microwave atomic clock, or you can turn it around. You can take one of the comb lines, lock it electronically to some very sharp atomic resonance, and then the repetition frequency becomes a known integer fraction of this optical frequency. So then you have an optical clock. These frequency combs have become standard tools for precision measurements. You can buy a complete system with all the electronics, and if you don't have so much space, you can even buy a turnkey frequency comb that fits on a desktop, where you come in through a fiber with light that you want to measure. And on a display, you can read out the frequency now automatically to as many digits as your reference stock will allow. So these are the frequency combs. There are many applications now beyond precision spectroscopy. But as I said, this tool, if you had had that to begin with, it would have saved 10 years in our efforts of spectroscopy. Now with frequency measurements, easy, of course, the focus has shifted on eliminating systematic errors and ruling out systematic errors as well as we can. And so the laboratory looks fairly complex, but in principle, we still do the same thing. So we produce our ultraviolet light now with a diode laser with 2 stages of frequency doubling, which you can actually buy commercially. We send this light into a cavity inside the vacuum chamber. We still have cold atoms, but now we can measure the frequency, we can stabilize the frequency, and we can measure the frequency in terms of an atomic clock using a frequency comb. And previously, it was actually difficult to find the resonance, this narrow resonance. So when I was had to search for some while because things drift, now with the frequency comb, you can park your laser on any point of the spectrum as you like. So this is an example of such a resonance. It's not symmetric, and that has to do with the second order Doppler effect. The atoms, even though they're at helium temperature, are still fast enough that we get relativistic line shifts. So to reduce this, we use longer delays, longer waiting times, and we look at a fraction of the atoms that are slow. Of course, we lose signal, but the line becomes more symmetric. And one can fit to this whole array of line profiles to find the actual unshifted frequency. And so this is has now been measured to within 10 hertz in published in 2 papers that are cited here. In this second one, I think we used cesium fountain clock at the Physikalisch-Technische Bundesanstalt in Braunschweig. And we had a fiber link sending, connecting PDB with our Garching laboratory. We had to take into account the height difference between the two labs to correct for gravitational redshift. But so this is a very precisely measured frequency. Of course, there are other clock transitions which you can measure even more precisely of heavier atoms that are easier to tame. But what makes hydrogen different is that we have a theory, a very detailed theory. In the simplest Bohr or Schrödinger model, the energy levels just scale with 1 over the principal quantum number squared in atomic units. If we include relativistic effects according to Dirac, the equation looks a little bit more complicated, where alpha is the fine structure constant, k depends on the angular momentum. But this does not take into account the fact that we have recoil, that is really a two-body system where both the electron and the proton move. So anyway, so you can expand this Dirac solution in terms of powers of the fine structure constant. But now we need to worry about the recoil. And so if you include recoil effect, it becomes more complicated. And of course, you need also to worry about relativistic recoil effects. So it becomes more complicated still. And we haven't even started to worry about radiative corrections, Lamp shifts. So if we include that, relativistic self-energy, vacuum polarization, 2-photon correction, 3-photon correction, radiative recoil correction, nuclear self-energy, polarizability, and nuclear size, we get things that looks cumbersome to humans, but easily understandable to computers. And the remarkable thing is that we have such a formula and that we, in fact, can calculate the predicted energy levels to very high accuracy. If we look at the various contributions, we see there is one effect that really spoils it, and that is the effect due to the finite size of the proton. So, and this size, this problem is something that, of course, we knew about. Murray Gell-Mann first postulated that the proton is not an elementary particle, but a composite system made up of quarks and held together by gluons. And Bob Hofstadter at Stanford was the first to actually measure the charge radius of such a proton using electron scattering. And so if you look at the history of the Rydberg constant, in the old days, we were limited by Doppler broadening of hydrogen lines. Then when we had Doppler-free spectroscopy, we were limited of the art of wavelength measurement. And finally, by the art of measuring the frequencies of light. But just when we had this fantastic tool of the frequency comb, it was impossible to make progress because now we were limited by the unknown, by not knowing the charge radius of the proton well enough. So how do you measure the proton radius? Well, I mentioned accelerator experiments, electron scattering, but that's not our craft. We can try to measure the proton radius from hydrogen spectroscopy. And we can take advantage of the fact that if we have two different transitions that we measure, such as the 1s2s transition and say the 2s8s or 2s8d transition, that with these two measured frequencies, we can determine two unknowns. The energy levels of hydrogen are given by the Rydberg constant in atomic units over principal quantum number square, plus the Lamp shift of the ground state over principal quantum number cube. And so with two measurements, we can determine these two quantities, and the ground state lamp shift by convention includes the effect of the finite nuclear size. So by comparing two transitions, we can in fact measure the proton size. And this was done over the years in many different experiments. And so here's an overview of all these results. And so what people did is they found some average value of the hydrogen world data that gave the size of the proton. But it was not so satisfying that we had to deal with such large errors. And so 20 years ago, some of us got together to say, let's try to measure the proton size more accurately by looking at muonic hydrogen. Muonic hydrogen is the brother of the hydrogen atom, where the electron is replaced by a negatively charged muon. And the muon is 200 times heavier than the electron. So all the energy levels are 200 times farther away. And the lamp shift actually is now in the mid-infrared. And unlike for hydrogen, the 2p state is a less tightly bound one because vacuum polarization dominates. But so the idea was, if we measure this lamp shift and observe the Lyman alpha decay at 2 kilo electron volt, then we should get a very accurate value for the proton size, because the muon energy is about 7 orders of magnitude more sensitive to the proton size than hydrogen. So here is a view of the experimental hall at the Paul Scherrer Institute in Switzerland, which here shows some bending magnet for velocity selection of slowed down muons, which are then injected into a superconducting magnet. And it was frustrating for a while because we only had limited beam time. The signal, a few events per hour, people worked around the clock, and there was no signal. The Paul Scherrer Institute was about to advise to terminate this experiment. Then I think the Nobel Prize helped, so we got another round. And in 2009, finally, there was a resonance. We could see the lamp shift in muonic hydrogen, but it was not where we expected it. And that explains why the earlier attempts failed. But so this was then a very accurate measurement of the proton size, but it's not in agreement with the hydrogen data. It's 4 sigma off. And if you look at the co-data value of the proton size, which includes electron scattering data, it's even almost 6 sigma off. And so this is what's known as the proton radius puzzle. And so the question is this something fundamental? Have we discovered a flaw in quantum electrodynamics? Or is it due to some problems with the experiment? And of course, it has stimulated a lot of speculation. If something is wrong, what could be wrong? There's more than 1,000 papers, theory papers, inspired by this proton size puzzle. I should say that in 2016, the experiment with Randolph Pohl as a spokesman also published a value for the charge radius of the deuteron. And it turns out that also the deuteron is smaller than expected. So where could the discrepancy come from? If you think of our hydrogen 1s2 as reference, the discrepancy would correspond to 40 line reads. So out of the question, this cannot be. If you think of the lamp shift resonance in muonic hydrogen, it would be 4 complete line widths. So that also cannot be. So if anything went wrong, it might have gone wrong in the spectroscopy of other transitions in ordinary hydrogen atoms. And for instance, if we look at the blue Balmer beta line, here the shift would correspond to only 7 times 10 to the minus 4 of the line width. So we went back and felt, let's investigate whether maybe something could have gone wrong in hydrogen spectroscopy. And so there is one experiment that we have done recently, that is to compare 1s, 2s with the blue Balmer beta line, the 2s4p transition. This is not a 2-photon transition. It can be detected by looking for Lyman gamma photons from the 4s state. And the results were published in 2017 by Axel Bayer and co-authors. The experiment is sketched here. So we start with our hydrogen 1s, 2s spectrometer, and then there is an extra laser now at 486 nanometers that gets expanded and is sent at right angles through the cold metastable beam and is precisely retro-reflected so that any linear Doppler shift occurs with 2 signs, so it should not make a big systematic problem. Here's a sketch of the experiment. So this is the blue light beam that crosses the atomic beam, and the Lyman gamma photons are detected with microchannel plates, and we have a segmented detector so that we can compare signals of photons emitted at different angles to characterize quantum interference effects, Fano-like effects, due to distant resonances that had previously been ignored. So that's described in this science paper. And so what was the result? So this is the Balmer beta line. And the result is no longer in disagreement with the muonic hydrogen. So it was felt that maybe the muonic radius is right, and there were mistakes in the earlier hydrogen spectroscopic measurements. So Axel Bayer and Lothar Meisenbacher shared the Helmholtz Prize in 2018 for this measurement. And the codata value of the proton charge radius officially changed. So previously, these are the world data, and now people believe that the muonic charge radius is right, but to be on the safe side, maybe allow for somewhat bigger errors. And so with this, the official value of the Rydberg constant has changed from 2014 to 2018. And if you look at the history of the Rydberg constant, now we overcame this obstacle. So now we have gained a whole order of magnitude in the accuracy of the Rydberg constant. But this is only one single measurement, and how sure can we be? So it's important to look at other transitions in hydrogen, also to check for the consistency of the quantum electrodynamic theory. And one transition that has been studied for more than 10 years in Paris in the group of Lucille Julien and François Pirabin and François Ney is a 2-photon transition from the ground state to the 3s state. And so this experiment was also carefully redone. And in 2018, they published a new value, much more precise, but in agreement with the old larger proton size. So then that means back to square one, if you like. In our laboratory, Alexei Grenin, for his thesis work, also measured this transition, but using direct excitation with a laser frequency comb. So he just defended his thesis a little while ago, and he finds a value that is not in such bad contradiction to the muonic radius. So then now it's 2 to 1, but of course one cannot be very satisfied. There is also a recent remeasurement of the original 2s2p lamp shift in the group of Eric Hessel's at York University. And they have published in 2019 a result that now agrees with the muonic radius. And also electron scattering data have been remeasured at Jefferson Lab. And in 2019, they had in Nature a publication that described the new, very careful measurement of the proton size, which now is in agreement with the muonic radius. So very likely, the answer is that the earlier experiments, they're flawed, and the real proton radius is smaller. But of course, we are scientists, we need to be sure. And so, as I mentioned, there are experiments still going on at Garching. In particular, Lothar Meisenbacher has measured the 2s6p transition now with a statistical uncertainty very much smaller than this. But the data are not unblinded yet, because he really wants to be sure that all systematic errors are discovered before one looks at the numbers, so that human bias doesn't play a role. And so what do we want to do? Well, as I said, we continue to look at other transitions in hydrogen. We want to find out why there is this discrepancy with the Paris experiment. Thomas Udem is looking at other hydrogen-like systems, in particular helium plus in an ion trap, which one can excite at 60.8 nanometers. We can ask, how far can we push hydrogen spectroscopy? Can we compare to an optical atomic clock? Well, movable, transportable optical atomic clocks are emerging, and very likely we can improve by another 1, 2, 3 orders of magnitude in direct comparison of hydrogen with such a clock. And that would, of course, give us an even more intriguing starting point for looking for possible differences between matter and antimatter. So this is the current status. I have to mention our team. These are people who have worked at Garching. The one in gray, I have moved on. Randolph Pohl is a professor in Mainz, still in use at Colorado State University. Nikolai Kolashevsky is actually the president of the Lebedev Institute in Moscow, and Arthur Matveyev has also moved to Moscow. But so we have still a core team of highly dedicated and enthusiastic people, and of course, they really deserve thanks for all this work. I need to thank the sponsors, such as the European Research Council, the Max Planck Foundation, and the Carl Friedrich von Siemens Foundation, who have allowed me to keep on working, even though I'm way beyond the ordinary retirement age in Germany. So with this, I thank you very much.